Stanford University.
Well, I think what I'm going to do is take roughly a half an hour or something like that and just discuss some elementary mathematics. Now, I want you to learn this mathematics, and if need be, to look it up. It's three simple pieces. See, three simple pieces of mathematics, all elementary, and I suspect most of you either know this or knew it at one time, but it's so central that I think we need to lay it out and use it. Use it, lay it out for future purposes. Okay. The first piece of mathematics is called Lagrange multipliers. How many people here have seen Lagrange multipliers? How many of those people remember what a Lagrange multiplier is? So roughly half the people who have seen it can use it. Would that be fair to say? How many people have never seen a Lagrange multiplier or can't remember what it is? All right, so the answer is the majority of you have, but I'm going to remind you anyway because it is absolutely central. We're constantly minimizing or maximizing things subject to constraints. What is the thing that we're likely to minimize, incidentally, or maximize, sorry? Entropy. But we'll get to why entropy, not tonight, next time, I suspect, but why we maximize entropy. But yes, thermal equilibrium is a state of maximum entropy, and that means we want to maximize something. As a function of something else, we want to maximize a certain function as a function of the variables that define it, number one. Number two, there are constraints. We don't just want to maximize a function, but we want to maximize a function subject to some constraints. What might the constraints be? Well, a particular constraint might be that we know the total energy of the system, or we know the average energy of the system. For some reason, we may know the average energy of the system. For example, we might have, again, a container full of a lot of molecules. We break it up into small pieces. We're going to study one small piece, and I tell you that the total energy in that container is whatever it is, 20 zillion joules. Okay. I also tell you that it's composed of a bunch of identical parts. How many identical parts? 10,000 of them. What's the average energy in each one? Well, you take the total energy and you divide it by the number of parts, and that tells you the average energy in each part. Now I want to focus on this part and say, I know the average energy, and I want to maximize the entropy subject to the constraint that the total energy is fixed. That's a problem. That's the kind of problem that emerges time and time again, over and over. Another example is we may know the total amount of electric charge in a region, and we may want to maximize the entropy given the total amount of electric charge, or the total amount of angular momentum, or whatever. So we constantly face problems of minimizing or maximizing. The mathematical subject of minimizing and maximizing are equivalent to each other, or the same. We constantly want to maximize functions of several variables subject to constraints on those variables. What does that mean? Example, a function of two variables. Let's literally take an example. I want to minimize or maximize? Minimize, I think, x squared plus y squared. Now, anybody can minimize x squared plus y squared. What's the minimum value of x squared plus y squared? 0. It can't be less than 0 because x squared and y squared are both positive. At x equals 0 and y equals 0, it is equal to 0, but it's not equal to 0 anywhere else, so the minimum is right at x equals y equals 0, and the function is equal to 0 at that point. Right? But now supposing I tell you I want to minimize it subject to a constraint. I want to know where x squared plus y squared is minimum given that, I don't know, let's say x plus 2y is equal to 1. Right. To draw a picture, we can plot on the plane here the contours of x squared plus y squared. X squared plus y squared, like a contour map. Right at the center, it's minimized, and as we move away, it forms a bowl, a valley, and the contour map would look like this. On the other hand, and of course the minimum of the function is right at the center. On the other hand, I won't really want to minimize it subject to a constraint, and that constraint is x plus 2y equals 1. That's a straight line, and I don't know, it's a straight line. Maybe it looks something like that. So what I'm really asking is where along this line is x squared plus y squared minimized given that you're on the line? Well, that's certainly not at the origin here. It's somewhere along here. Looks like it's about over here, doesn't it? X squared plus y squared, of course, is just the squared distance from the origin. And so you're kind of asking along this line, where is the line closest to the origin? That's the geometric problem that corresponds to it. But the mathematics problem is to minimize x squared plus y squared subject to a constraint that x plus 2y is equal to 1. How do you do that? Well, one way would just be to eliminate, let's do it. We could eliminate one of the variables, plug it into here, and then minimize the remaining function. For example, what does that mean? We could solve for x and find that x is equal to 1 minus 2y, and then plug it into here, and we would have 1 minus 2y squared, that's x squared, plus y squared. Let's just call this f. F on the line, on the red line, f would be given by this, and then the next step is just to minimize f with respect to y. We don't have to worry about the constraint anymore because we've already taken the constraint into account. So that's one way of doing the problem. Now, in many cases, the constraint is just too complicated to solve. It might be some stupid, complicated function that's just too complicated to solve. But there is another way to do the problem. And the problem is called the method of Lagrange multipliers. Perhaps as we go along, I will prove that it works for a simple, well, not for this example, but maybe a little more general example. But let me just tell you what the method is. I'm going to tell you the rule. Then we can try to see maybe why the rule is true. All right, what you do, here's our problem. We have a function of some variables, in this case just 2, function of x and y, and we want to minimize it, given that some other function, g of x and y, is equal to 0. G of x and y, in this case over here, just corresponds to, what was it? X plus 2y minus 1. X plus 2y minus 1 is equal to 0. That's the constraint. All right, here's the trick that you do. You take the constraint and you multiply it by a new variable. The new variable is often called lambda, usually a Greek letter, and it's called the Lagrange multiplier. You add that to f. Add or subtract, it doesn't matter. You add it to f, and now you have a new function of x and y that also depends on this auxiliary variable, which we're going to get rid of soon enough. We're going to get rid of it in a moment. But we have a new thing, which is f and lambda g. And then what we do is we just minimize f plus lambda g with respect to x and y, ignoring the constraint. Forget the constraint and just think of this new object here and minimize it with respect to x and y. Okay, how do you minimize a function of two variables with respect to its variables? You differentiate with respect to the variables and you set the result equal to 0. So that would say we differentiate df by dx plus lambda. Lambda is treated as just a constant times dg by dx. And we set that equal to 0. That's one equation. And the other equation is df by dy plus lambda dg by dy is equal to 0. Those are the two equations for minimizing this particular object over here. All right. Here are two equations for two unknowns, x and y. Both of them depend on x and y. X and y, x and y. And we can solve them for x and y. But wait a minute, we have this thing lambda there. What do we do with that thing lambda? All right. The answer for x and y will depend on this parameter, lambda. What we do with the parameter lambda at the end, after we have solved this problem over here, implicitly in terms of lambda, is that we set lambda to whatever value is necessary in order that the constraint, the original constraint, g equals 0, is really satisfied. I'm going to give you an example. I'm going to show you how it works by example. In fact, we might as well do that example, and then I'm going to show you why it works. Show you how it works, and then why it works. Okay. Incidentally, you could imagine having more variables, x, y, z, w, and have several constraints. I'll tell you later on what you do with several constraints, but let's just do it as a function of two variables for one constraint. Okay, so let's solve this problem up here. Here's our problem. Minimize x squared plus y squared subject to the constraint that x plus 2y minus 1 is equal to 0. Well, we add this quantity, x squared plus y squared plus lambda times the constraint, x plus 2y minus 1 in this case. The 1 is not going to be very important to this calculation. That's a new object, and now we minimize it. How do we minimize it? We differentiate it with respect to x and set the result equal to 0. What's the derivative of this? That's 2x plus lambda x equals 0. We differentiate with respect to... Oh, sorry, plus lambda. Good, thank you. Plus lambda equals 0. 2x plus lambda equals 0. And then, same thing with y, 2y. And in this case, it's plus 2 lambda, extra 2 here, equals 0. Now we can solve for x and y in terms of lambda. We don't know what lambda is yet, but let's solve it in terms of x and y. Let's solve for x and y in terms of lambda. X is equal to minus lambda over 2. That's this equation. X is minus lambda over 2. And y, I think, is just equal to minus lambda. Everybody agree with that? Right. OK, so we've solved our problem, except we don't know what lambda is. What we do now is we choose lambda so that the constraint is actually satisfied. Let's do that. X plus 2y minus 1 is equal to 0. Let's plug in the solution. The solution is x, which is minus lambda over 2, this one, plus 2y, which is minus 2 lambda, I believe. 2y is minus 2 lambda. Minus 1 is equal to 0. Sorry, is equal to 1. Is equal to 1. I just transposed the 1 over to the other side. And now, what does that mean in terms of lambda? Excuse me. 2 is 4 over 2. Okay, so this is what, minus 5 halves lambda? Minus 5 halves lambda equals 1, or lambda is equal to minus 2/5. And now we solved our problem. Lambda is equal to minus 2/5, which means lambda over 2 is, minus lambda over 2 is 1/5, I think. Let's see, lambda over 2, yeah, is 1/5, and y is equal to 2/5. I've just plugged in what lambda is. Minus lambda is 2/5, minus lambda over 2 is 1/5, and we have now found out where this curve, or where this line achieves its closest distance to the origin. That was the mathematics problem. Minimize x squared plus y squared, which is just the square of the distance of a point to the origin. Minimize it along this line, and that means find the point along the line which is closest to the center. Right. Now, we could check independently, of course. We could do the calculation the other way by eliminating the constraint, by solving the constraint for one of the variables and plugging it back in, and we could do it that way. Of course, we'll get the same answer. Let me show you why this works. So just a little bit of algebra. It just takes a little bit of algebra to see why it works. And it's very general. It's extremely general. It's not x squared plus y squared was just an arbitrary function that I picked. Pick any other function. The fact that I chose the constraint to be a straight line, a linear function, again, nothing special about that. Okay, let's do the problem, not this problem, but a general problem in both ways and see that we get the same answer. Right? So let's start by the method of eliminating one of the variables from the constraint. Here's our problem. We have f of x and y. We want to minimize it subject to the constraint that g of x and y is equal to 0. G of x and y equals 0 is some curve, and it means we're minimizing f along that curve. All right. Here's the way I'm going to do it. I'm going to imagine, it may be too hard to do, but it doesn't matter. All I have to do is imagine doing it. Solving this equation for one of the two variables. Which one? All right, let's imagine solving for y. If we solve this equation for y, it will tell us what y is as a function of x. In other words, this was some curve. It corresponds to a curve that represents y as a function of x. Let's not worry right now whether it's single-valued, not single-valued. That's not an important issue here. It gives us a y as a function of x. Then we plug that back into here. And when we say what we're really trying to minimize is f of x and y of x. This is now a function of a single variable. It's only a function of x because y is now a definite function of x. F of x and y becomes f of x and y of x. Okay. Next step. What's the next step? Differentiate this with respect to x and set the result equal to 0. That will find us the minimum of x subject to the constraint. So let's do that. We have to differentiate the x dependence, that's df by dx. But then we have to add to that the derivative of f with respect to y times dy by dx. This is an ordinary derivative, dy by dx. All right, this is the change in f when we change the first argument here of the function, and this is the change due to the change in y, but the change in y is determined by the change in x. Okay? And we set this equal to 0. Okay, that's an equation. But what about dy by dx? What do I know about dy by dx? Let's see what we can figure out about dy by dx. This curve here is a curve of constant g. Let's imagine moving along it. Imagine moving along it and making a small differential displacement. A small differential displacement along the curve of constant g will not change g. By definition, if we're moving along the curve of constant g, then g doesn't change. So I can write the following equation. Along this curve, the derivative of g with respect to x times dx plus the derivative of g with respect to y times dy is equal to 0. That says g doesn't change when I make a small differential displacement. The reason I did this is because this allows me to solve for dy by dx in terms of things involving the constraint g. All right, so dy by dx, we just divide by dx. And what do we get? We get dy by dx. Dy by dx is equal to minus dg by dx divided by dg by dy. Right, very simple. We just use the statement that the constraint, along the constraint, g is constant, and that tells us something about the derivative of y with respect to x along that curve. And now we plug it in. We plug it into here. Let's see what we get. dy by dx, well, might as well write it over. We get df by dx. Now there's going to be a minus sign from the dy by dx, so let's put the minus sign here. Df by dy. And now dy by dx, except I already took into account the minus sign. This is dg by dx divided by dg by dy. Let's put it in there, dg by dy equals 0. Let's multiply by dg by dy. So we get dg by dy equals 0. That's not a bad looking equation. That's the equation after we've eliminated y. This is the equation which solves for the minimum of f subject to g. What I want to show you, I don't want you to use this. We're not going to use this. What we're going to do is show that you get exactly the same relationship from the method of Lagrange multipliers. Okay? So let's go to the method of Lagrange multipliers. Here are the two equations that followed from the method of Lagrange multipliers. But now let's eliminate lambda from the equation. How can we do that? We can solve for lambda in one equation and plug it into the other. All right, so let's see. Here lambda, it says lambda is equal to minus df by dx divided by dg by dx. Is that right? Let's see. Yeah. Minus, because I've got the transpose, and then lambda will be df by dx divided by dg by dx. Now let's plug it into here. All right, let's plug lambda into here. So we have lambda minus sign df by dx divided by dg by dx. But instead of dividing by dg by dx over here, let's just multiply by dg by dx over here. All right, it really was divided by dg by dx, but then I just multiply. The right-hand side is 0. Okay. Hopefully it's the same equation. I'm not even going to look. I hope it's the same equation. Is it the same equation? Hmm? They both have minus sign. Hmm? They're both equal to 0. Right. We have to multiply by -1 to get them to be the same, but they are the same. All right, so this was just a simple illustration that the method of there's an intuitive geometric picture of it, but it takes longer to explain than just to do the arithmetic. The method of Lagrange multipliers is completely equivalent to solving the constraint and then plugging back in, and it's usually easier. Okay, so what are the rules again? You take the constraint, you multiply it by lambda. You add it to the thing that you're trying to make minimum or maximum. You then differentiate as if you were trying to minimize the whole thing. All right. You get two equations, let's say, or however many equations there are variables in the problem. Doesn't have to be two. Okay, so the other one is df by dy plus lambda dg by dy equals 0. You solve those two equations. They're two equations for two unknowns, x and y. But then, after you're finished, you choose lambda so that the constraint is actually satisfied. So that the constraint g equals 0 is satisfied. So I gave you some an example. Make up your own examples. Work out, I don't know, instead of x squared plus y squared, take x cubed plus y cubed. And the constraint is that sine of x plus y is 3. I don't know. No, the sine of x plus y can't be 3. E to the x plus y is equal to 3. Right. All right. Just make up an example or two. Try doing it by eliminating one of the variables, and you'll quickly discover that it's usually easier to just use the method of Lagrange multipliers. But then one of the nice things about the method of Lagrange multipliers, it doesn't force you to single out one of the variables for special treatment. The method that I used here singled out x as opposed to y. It wasn't special, but I singled it out to solve for it. I solved for y, actually. And so I didn't treat the variables symmetrically. No problem, there's nothing wrong with that. But it's a nice feature of the method of Lagrange multipliers that it treats the variables symmetrically. Let me just tell you, without proving, supposing I had a function of several variables. Function of x1 dot 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 xn, whatever they happen to be. And now I have a collection of constraints, not just one constraint. For example, I may have two constraints. One of the constraints might be that the total energy is fixed. Another constraint might be that the total charge is fixed, or the energy and the angular momentum. There would be two separate constraints. And so I would have a set of constraints, g1, let's call it, is equal to 0. g1 is a function of the same set of variables. g2 is equal to 0, however many I have. It's important that there not be more constraints than variables. Otherwise, you can't solve it. If you have more constraints than variables, in general, there is no solution. But fewer constraints than variables. Then what you do is you introduce a Lagrange multiplier for each of the constraints. So you write f plus the first Lagrange multiplier times g1 plus the second Lagrange multiplier times g2. And however many Lagrange multipliers you have, or however many constraints you have, and then you minimize or differentiate the result with respect to the x's, set them equal to 0, the f plus the sum of lambda I gi with respect to each one of the x's and set it equal to 0. Solve it, and then choose all of the lambdas. How many lambdas do you have? One for each constraint. Choose all of the lambdas so that all the constraints are satisfied. That's the method of Lagrange multipliers, and as I said, It is central to statistical mechanics. We will use it over and over again. And if you're not familiar with it, just look it up on, I'm sure you can find it easily on the, just Google it, Lagrange multipliers. It's probably a Wikipedia article. And try it out, work with it a little bit, and become familiar with it. I will not explain it again, but I will use it again, over and over. What is the thing that we're typically going to minimize? The entropy. What are the constraints? Constraints such as we know the total energy, we know the total whatever it happens to be. Okay, next little theorem. These things are too small to really be called theorems. Stirling's approximation to the factorial function. Everybody know what Stirling's, anybody not know what Stirling's approximation is? Anybody not know? Oh, no, but I mean, do you know how to prove it? Okay. Where it comes from. All right, so let's just review very quickly Stirling's approximation. N factorial occurs over and over in all sorts of probability contexts. Every time you calculate permutations and combinations in order to calculate probabilities, N factorials appear all over the place. Okay? Generally, the n's which appear are very large numbers. They have to do with how many ways there are arranging or rearranging a large number of variables in some large number of ways. And so it's important to have an approximation, of a reliable approximation, which becomes better and better as n becomes large for the factorial function, n factorial. Equals 1 times 2 times 3, dot, 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 up to n. That's the factorial function, right? All right, now I want to find a good estimate for it. What I'm going to begin with is by taking its logarithm. I'm going to estimate the logarithm of n factorial. Once I've estimated the logarithm of n factorial, how do I estimate n factorial? We exponentiate the logarithm, right? So it's just as good to, all right, so let's estimate the logarithm of n factorial. Log n factorial, that's equal to log of 1 plus log of 2 plus log of 3 plus and so forth and so on. Log 1 happens to be 0. But nevertheless, write it down, plus log 2 plus log 3 dot, 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 plus log n. All right, so what do I have? Let's plot in this direction. Let's plot logarithm of n. Now, what does the logarithm function look like? It looks like it's 0 at n equals 1, and it looks something like this. And basically what we're doing is we're adding up the areas n equals 1, n equals 2, n equals 3, dot, dot, dot. We're adding up the areas under this logarithm curve here. All right. When n becomes large, it's a good approximation to the sum to replace it by the integral. Right, the integral. So let's consider then, instead of considering the sum here, this is sum of log of n from n equals 1 to n equals, sorry, it's log of, let's call it log of x. Log of x from x equals 1 to x equals n. And we're going to replace that by integral dx logarithm of x. Okay, so we have the problem of integrating logarithm of x. It's easy to do. You just look it up in a table of integrals. That incidentally means find a function whose derivative is logarithm of x. I'll tell you how I would think about it if I didn't know the answer. I would begin by saying, well, logarithm, at least for large x, is a very slowly varying function. It practically doesn't vary at all. Logarithm is a terribly slowly varying function. So I might just try saying, well, what if this logarithm were a constant? Then what would be the integral dx of a constant? X times the constant, right? X times the constant. OK, so let's try x times log x. X times log x. If log x were a constant, and it's very, very slowly varying, if we replaced it by a constant, then the right answer would be x times the constant. Right? So this shouldn't be too far off. Now let's differentiate it and see if we really get logarithm of x. All right, so what's the derivative of x log x? Well, it's got two factors. So the derivative of the first factor is 1 times the second factor. That gives us good. That gives us log x, right? But there's another term. What's the other term? It's x times the derivative of logarithm of x. But the derivative of logarithm of x is 1 over x. OK, so what do we get? Plus 1. Not log x plus 1, but log x, 1 plus log x. So that's not so good. We wanted to get log x. We didn't want to get 1 plus log x. Okay? But all we have to do now is to subtract something from this whose derivative is 1, which is x. That, my friends, is the integral of log x. X log x minus x. Differentiate it, you'll get x. You'll get log x. So we now know that this integral goes from 1 to n. And the answer is n log n minus n. I've just substituted for x. I've just integral from 1 to n. One endpoint just gives 0. The other endpoint gives n log n minus n. This is Stirling's approximation for the logarithm of n factorial. And actually, this is the way we're going to wind up using it, n log n minus n, because we're generally going to be interested in the logarithm of n factorial. But just to I don't know what's going on. Just to complete the calculation, we now want to exponentiate it. All right, so we want to take e to the n log n, e to the minus n. We have the sum or the difference of two terms. When I exponentiate it, I will get e to the n log n. That's e to the, what's e to the n log n? That's n to the n. Same as n to the n. N to the n is the same as e to the n log n times e to the minus n. This is Stirling's approximation. Stirling's approximation to the factorial function. It grows very fast. N to the n grows very rapidly, but not quite as rapidly as n to the n. It's modulated by a decreasing function, e to the minus n. OK, so that's a second little lemma or theorem that you must know in order to do statistical mechanics. And the third one is a combinatoric fact, simple combinatoric fact, but one, and once we do it, we won't do it again, or we won't explain it again, but let's do it anyway. I'll tell you what the problem that we're really interested in. Supposing I have n copies of the same system. Now you can just think of this as n boxes. N boxes, and each box can be in a state. The states of a single box, I'll label them over here. They actually correspond to the energy states of the system. But here they are. Vertically is energy. This is the ith state over here. And each one of these boxes can be identified with a state in here. In other words, each box is in a state or has a particular state labeled by one of these i's. We could draw a picture, or we could draw a figure. If the first box happens to be in this state over here, I'll put a line over there like that. If the second box happens to be in the same state, I'll put another line over here. Supposing the third box is in a different state over here, and the fourth box is in yet a different one over here, and the fifth box, let's put a fifth box in just to add one more, just happens to be in the same state as this one over here. All right. So a diagram like this is a description of the states of n copies. There are n copies here of a system, n copies, each with its own state. Now, here's an interesting quantity. Oh, what shall we label? Yes, we labeled the states I. Notice that I does not stand for which box we're talking about. It stands for the possible state within a box, the possible configuration within a box. And I'm taking them to be discrete. All right. I can ask, how many boxes are there in the first state? This is I equals 1. How many boxes are there? Well, in this case, there are no boxes with I equals 1. But in general, the answer will be an integer, n sub 1. That's the number of boxes in state number 1. The number of boxes in state number 2 is n sub 2, n sub 3, and so forth. What do these n's have to add up to? I wonder if the lecturer is supposed to be in here tonight. It's supposed to be in the other room, no? Yeah, okay. Okay. What must these n's add up to? Big N. The number of boxes in the first state plus the number of boxes in the second state plus the number of boxes in the third state and so forth have to add up to n. But the question I want to ask is, how many ways are there of choosing a state for each box such that there are n1 boxes in the state 1, n2 boxes in the state 2, n3 boxes in the state 3, and so forth? How many ways are there of getting a given set of n's? Okay. Anybody know the answer? Oh, I wrote the answer down in the, yeah, the answer was written in the notes, so you do know the answer, I presume. Okay. Let me write the answer down, and then if we have time, I'll try to explain why it's the answer. The answer involves a bunch of factorials and is the primary reason why I bothered giving you an approximation for the factorial function. All right, the answer is very simple. It's simple, but subtle. It's capital N factorial. What shall we call this thing? I think I just called it, I don't remember, did I give it a name in the notes? The number of ways of distributing a state to each box such that there are n1 boxes in state number 1, n2 boxes in state number 2, and so forth and so on. I'll just call it number. Right. It is equal to capital N factorial divided by a product. And the product is and 1 factorial, and 2 factorial, and 3 factorial, dot, dot, dot. What happens if some of the states are unoccupied altogether? For example, this state over here doesn't appear in any of these boxes. Let's call this the 42nd state over here. What is n sub 48? 0. That looks a little odd. A 0 factorial downstairs. But what's 0 factorial? 1. That's the definition of a factorial function. So all of the unoccupied states just give a bunch of 1s. 1 times 1 times 1 times 1 is just 1. So you only get something interesting from the states which are actually filled. And if there are 3 boxes in the first state, then there's a 3 factorial. 4 boxes in the second state, then there's a 4 factorial, and so forth. All right, this is the answer to the question of how many ways there are of making a configuration where there's a given number of boxes in each state. Let's see if we can at least motivate the answer. I wonder if we should just go in there and get some seats. Yeah, I think that's the thing to do. If we come in a little early next time, I'll finish up the derivation of this 10 minutes early. But you can also look it up again, Wikipedia.
For more, please visit us at stanford.edu.